Welcome to the deep dive. It's really great to have you sitting in with us today.
Always a pleasure to be here.
We're always looking for those topics that give you that genuine aha moment, the kind of insight that makes you look at the physical world just, a little bit differently.
Right, the stuff that really shifts your perspective.
Exactly. And you're here because you love gaining a deeper understanding of complex systems, and you appreciate doing it without having to wade through a swamp of dense academic jargon.
Nobody wants that.
No, they don't. Well, today we have an incredibly specific and somewhat controversial mission. We are diving into a very unique stack of sources you've shared with us. It's a highly detailed 62-page dialogue accompanied by a robust set of Python simulation data.
Yeah, it's quite the package.
Together, these documents propose what the author describes as a massive paradigm shift in how we understand physics.
It really is an ambitious set of documents. I mean, what we're looking at is a radical reinterpretation of Einstein's special relativity, specifically focusing on the famous Michelson-Morley experiment. Right.
The sources referred to this entirely new analytical framework as the cyanide chat theory. And what makes this deep dive so fascinating is not just the theory itself, but how the author uses computational geometry to challenge concepts that have been standard in physics textbooks for over a century.
Okay, let's unpack this. Our mission for you today is to explore how this cyanide chat theory claims to remove the magic from standard physics.
The magic, yeah.
When I say magic, I'm talking about the well-known relativistic concepts that space physically shrinks and time physically slows down when objects move at high speeds. Now, to be clear from the jump, we aren't here to declare standard physics obsolete.
Definitely not. We're just reporting what's in the documents.
Right, we are here to map out the author's argument for you. According to the source, instead of relying on abstract math that simply balances the equations, this framework attempts to reveal a hidden geometric structure behind relativity.
Like a mechanical explanation. Yes. The author treats this century-old physics problem like a locked room mystery, trying to find a physical mechanism for why these equations work the way they do.
That's a crucial distinction to make. The cyanide chat theory doesn't throw out Einstein's mathematical results.
It doesn't.
No, the calculations regarding length contraction and time dilation, they still hold up in the equations. Instead, the author posits that standard physics is missing the physical mechanism, the actual how and why these phenomena appear to happen.
So the math is right, but the reason is wrong.
According to the documents, yes. The answer lies in how our instruments actually sample information in three-dimensional space, rather than how the objects themselves physically behave.
To really get our heads around this, we have to go back to the bedrock of relativity, the classic Michelson-Morley experiment. Let's visualize the setup. Imagine a device called an interferometer.
A classic piece of hardware.
It's roughly 3 meters wide, and it's designed to shoot light back and forth to measure its speed. In standard thought experiments, physicists generally picture this device sitting flat on a standard 2D Cartesian plane.
Right, and this raises an important question within the context of the author's argument. Why default to a 2D plane?
Because it's easier to draw.
Essentially, yes. And according to the source material, this is the fundamental flaw in how traditional physics has approached the problem for over 100 years. The author argues that physicists have historically treated this flat, 3-meter device using a God's eye view.
A God's eye view, okay.
Yeah, by isolating the experiment to that flat plane, they assume that the entire surface of the device exists in the exact same temporal moment.
Like it all happens right now.
Exactly. They imagined a simultaneous now across the whole 3-meter width, assuming zero process, zero delay, and completely ignoring the physical history of how the light actually arrived at the device.
I want to make sure I'm following the author's logic here. They're saying that because early physicists couldn't easily model complex 3D spherical light propagation, they just flattened the experiment out for the sake of the math.
Essentially, yes. The argument is that they stripped away the depth of reality, they ignored the z-axis, and the cyanide chat theory's primary intervention is bringing that massive scale contrast back into the equation.
We have to zoom out.
Way out. To understand the proposed reality, we can't just look at this tiny 2D device in isolation. We have to introduce depth.
And the scale they introduce is mind-bending. I want you to picture this. Imagine that tiny 3-meter device is sitting at the exact center of a gigantic invisible sphere. And when the author says gigantic, they are not exaggerating.
Not at all.
This sphere has a radius of exactly 300,000 kilometers.
That specific number, 300,000 kilometers, is the foundational constant of this theory. It is exactly the distance that light travels in a vacuum in one single second.
So a 1-second sphere.
Right. The author calls this outer spherical shell the public space. You can conceptualize this public space as a massive, absolute canvas of raw information.
Raw data just waiting out there.
Exactly. It is the boundary where the raw data of the universe originates, effectively acting as a starting line for light before it begins its journey inward toward the observer, or, the device sitting at the center.
So we have this massive sphere of raw info, and it's all shooting inward toward our 3-meter device. This brings us to what I think is one of the most brilliant distinctions made in the text. Usually when we think about the interferometer, we only think about the light bouncing horizontally inside the device itself.
The bouncing light.
Yeah, the author calls this the experiment ray, but the source argues that by hyper-focusing on the experiment ray, traditional physics completely ignores the engraved ray.
What's fascinating here is how the author defines this engraved ray. These are the light rays traveling from that massive 300,000-kilometer outer shell, the public space, straight down into the center toward the hardware.
Coming from the boundary.
Right. And here's the critical part. As they travel, the author argues they carry an absolute timestamp of the exact moment they departed the shell. They are bringing a 1-second-old history lesson directly to the surface of the device.
Let me stop you right there to make sure I'm visualizing this correctly. The claim is that standard physics just ignores the journey of the light to the device and only cares about what the light does once it's already inside the device.
According to the critique in the source material, yes. Standard relativity treats the local frame of the device as an isolated system. But the Zayanachet theory insists we have to account for the absolute timestamps arriving from the public space.
Because it takes time to get there.
Because when those engraved rays come down from a giant 300,000-kilometer sphere and hit a flat 3-meter disk, they do not hit the entire surface of that disk at the exact same moment.
Right, because of the geometry. If you picture a flat 3-meter disk sitting inside a giant sphere, the edges of the disk extend outward. That physically brings them a tiny fraction closer to the incoming spherical wave of light.
They stick out.
Yeah, they stick out into the sphere. The exact center of the disk is sitting perfectly at the origin point, making it slightly further away from the expanding shell than the edges are.
Exactly. It's a minuscule geometric difference, but when you are dealing with the speed of light, it changes the entire structural map of time on the device.
It's no longer a flat now.
Right. The sources provide concrete numbers for this geometric arrival. According to their calculations, there is a 10 nanosecond difference between the light hitting the edge of the device and the light hitting the center.
That is such a cool detail. It means that, according to this framework, time on the surface of the device isn't a flat, perfectly simultaneous plane like the God's eye view assumed.
It's curved.
It is actually a series of concentric circles radiating inward. It's a 10 nanosecond thickness or gradient of past timestamps.
That 10 nanosecond gradient is the linchpin of the author's argument. It shatters the assumption of simultaneous time on the hardware. The outer edge is experiencing a timestamp from the public space that is 10 nanoseconds newer than the timestamp hitting the center.
So the outside is living in a slightly newer past than the inside.
The entire device is bathed in a gradient of temporal history.
Let's use an analogy to really lock this geometry in for you. Imagine you are standing in the exact middle of a massive, perfectly circular stadium. Every single person in the stands is holding a flashlight.
Okay, I like this.
And they all turn their flashlights on at the exact same absolute time, even though they all flashed at the same. Now, if you are holding a flat, wide net to catch the light, the geometry means you are catching different parts of that light wave at slightly different micro moments.
Because your net isn't shaped like the stadium.
Right. You are experiencing a sequence of events based entirely on your shape relative to the stadium.
That perfectly illustrates the concept. The light hitting you is engraved with its travel time. When the device is completely stationary, this gradient of time forms perfect, symmetrical, concentric circles. It's stable.
A nice, stable target.
But the real friction, and the core of the author's paradigm shift, occurs when we introduce velocity.
Here's where it gets really interesting. So if the gradient is stable when stationary, the obvious next question for the author is what happens to these timestamps when we apply velocity? Say, moving the device at 60% the speed of light, or 0.6 c.
When the device begins to move at 0.6 c, the geometric relationship to the public space undergoes a radical distortion. Because the device is moving forward through the field, it is literally running toward the light arriving from the front of the public space shell.
It's crashing into the light.
And conversely, it is running away from the light, trying to catch up to it from the back of the shell.
Wait, if the device is rushing forward at 60% the speed of light, how drastically does that actually change the timestamps? We are still talking about fractions of a second, right?
We are, but the fractions are massive in relative terms. The sources provide the exact data points for this moving scenario. Because the device is rushing forward at 0.6c, the front edge of the device intercepts the incoming light much earlier than it would if it were stationary.
How much are...
Instead of waiting the full 1 second for the light to travel from the 300,000-kilometer shell, the front edge meets the light after only 0.625 seconds of travel time.
That is incredibly fast. But the back of the device has the exact opposite problem, doesn't it? It's actively fleeing the incoming information.
Precisely. The light from the rear of the public space shell has to chase the device. By the time that light finally catches up and hits the back edge of the device, it is older light.
How old?
According to the author's math, it has been traveling for a full 2.5 seconds.
Let me stop you right there to make sure I'm fully digesting this. You're saying that under this theory, the front of a single 3-meter table is existing in a timestamp from 0.625 seconds ago.
Yes.
While the back of that exact same table is existing in a timestamp from 2.5 seconds ago. That is a massive skew in reality.
It is a profound skew. Structurally, the sources compare this to the Doppler effect, but with a critical twist. Instead of velocity compressing and stretching sound waves to change the pitch of a siren, velocity is compressing and stretching the temporal timestamps arriving from the public space.
So the movement at 0.6c is warping the timestamps of reality itself. Those perfect, symmetrical, concentric circles of time we had when the device was stationary. They're gone. They are violently skewed. The temporal map is squished at the front and elongated at the back because the device is swimming through a warped gradient of past information.
If we connect this to the bigger picture, this skewed gradient is the exact foundation the author uses to attempt to solve the grand illusion of Lorentz contraction.
The famous shrinking effect.
Right. As you know, for over a century, standard physics has taught that if an object moves at a significant fraction of the speed of light, the physical matter of the object contracts in the direction of motion.
Things get shorter.
The Zion-Adshat theory argues that this physical contraction does not happen, and it relies on what the sources call the double stamp concept to make its case.
The double stamp. This is where the Python simulation data really shines. Walk us through how the author uses this dual timestamp concept to prove, or rather to argue, that length contraction is an illusion.
The double stamp acknowledges that there are two distinct moments in the life of this data. The first stamp is the absolute moment when the light departs from the giant 300,000-kilometer public space sphere.
The starting gun.
The second stamp is the exact moment when the moving 3-meter device actually catches that light. To understand how the author maps this, we have to look closely at the simulation they built.
Yes, I want to spend some real time visualizing this Python simulation because it is the absolute climax of the 62-page document. In the data visualizations provided, the author generates two very distinct shapes to represent what is happening at 0.6c.
Two very important shapes.
A yellow circle and a magenta, or red-purple ellipse. Let's start with the parameters of the yellow circle. What is the simulation actually plotting here?
The Python script plots the yellow circle to represent the actual physical hardware of the 3-meter device existing in Cartesian space. It is the metal, the glass, the atoms of the interferometer.
The real physical object.
And the massive revelation from the author's data is this. When the velocity variable in the code is cranked up to 0.6c, the yellow circle does not change shape.
Let me repeat that for everyone listening. According to the simulation, the physical device does not shrink at all. It remains a perfect circle, 3 meters wide.
It stays completely intact.
The structural integrity of the matter is completely unaffected by the speed. So if the author claims the hardware doesn't physically squish, what exactly is the Python script plotting with the magenta ellipse?
This is where the concept of 4D to 2D mapping comes into play. The magenta ellipse is a map of the timestamps. The simulation asks a specific question. What happens when you map out only the specific points on the moving device that happen to share the exact same past timestamp from the public space?
Oh, I see. Because the device is moving at 0.6c, it is crashing into newer light at the front and running away from older light at the back. So the temporal map is a mess.
Exactly. The device is cutting through a staggered history. To find points on the physical hardware that all share the exact same temporal history, a true simultaneous moment from the perspective of the incoming data, You have to draw a line that connects different parts of that skewed temporal gradient.
And when the Python code plots that specific map of simultaneous time, it forms an ellipse. It is squished in the direction of motion. In the simulation's math, the radius of this simultaneous time map shrinks from a 10 down to an 8.
The author's conclusion here is deeply provocative. They argue that what Einstein and Lorentz actually calculated mathematically was the magenta ellipse.
The map of the timestamps.
They successfully calculated the mathematical map of simultaneous information. But because standard physics was historically trapped in the 2D God's eye view, because they lacked the computational tools to map the z-axis and the 300,000-kilometer journey of the engraved rays, they mistakenly believed that the magenta ellipse was the physical device.
They looked at the math of the timestamps shrinking and assumed the physical yellow circle was literally morphing into the magenta ellipse.
That is the core of the Ziana chat theory's critique. The author posits that Lorentz contraction is an illusion born of a category error. It is not the physical squishing of matter. It is a geometric cross-section of information scanning.
Information scanning. I love that phrasing.
It is simply the mathematical artifact of how a moving three-dimensional window, our device, samples four-dimensional temporal information coming from the public space and flattens it onto a two-dimensional observational map. The hardware stays perfectly round. Only our map of simultaneous time contracts.
So what does this all mean? If we step back and look at the entirety of this 62-page argument and the simulation data, the author is offering us a framework that attempts to restore a kind of mechanical logic to physics.
It really is a shift back to physical intuition.
They are arguing that we don't need to accept a universe that behaves like a funhouse mirror where space bends and matter swishes for no intuitive reason. Instead, they propose a universe that runs on rigid, beautiful, geometric procedures. It's all about the mechanics of information.
Right, data transfer.
It's about how long it takes data to travel from a massive absolute space to our tiny moving observational windows.
It replaces a physical paradox with a geometric procedure. It attempts to ground the abstract, often unintuitive math of relativity in the concrete geometry of sampling rates and data arrival times. But as with any theory that challenges a century of established science, answering one profound question immediately opens the door to another.
Always does.
I want to leave you with a final thought to mull over.
I love these. Lay it on us.
Throughout this entire exploration, the author has argued that length contraction is merely a geometric illusion, an artifact of how a flat map processes 3D space. If that is true, and the physical matter of an object does not actually compress when it travels at near light speed, what does that mean for the future of interstellar engineering?
Oh, wow.
For decades, our theoretical models for deep space travel have assumed that a ship moving at a fraction of the speed of light would physically contract, which radically alters our assumptions about structural integrity, shielding, and the physical distance to stars like Alpha Centauri. If relativity is just a symptom of our observation, and the ship remains perfectly intact and the physical distance remains absolute, do the engineering requirements for humanity reaching the stars fundamentally change?
Now that is an incredible implication to think about. If the magic is gone, the engineering has to step up. Thank you so much for exploring this highly complex stack of sources with us today. We love taking these deep dives with you, navigating these wild new paradigms, and we cannot wait to see what fascinating materials you share with us next time.